In today's lesson, we are going to estimate the definite integrals using trapezoids. Your essential question: how do you estimate the value of a definite integral by dividing the region under the curve into trapezoids? So let's first review our trapezoids. So I've given you an image of a trapezoid. A trapezoid is a four-sided figure with two bases. Those two bases are always parallel to each other. So we could call this base 1, I'll use B1, and we'll call this base 2 or B sub 2. The height is always perpendicular to your bases, so this height here we'll call H. Now your trapezoids could be in different orientations. So if you go over here to the right, I have a trapezoid that's been drawn under a curve, and it is on its height. The height is tangent now to the x-axis. So this part right here is your height. And the way that you would find the length of that height is you could take your value for x1, your value for x2, and you could subtract them or find the difference. Then the two vertical pieces here, those end up being your bases. And the way that you find those lengths is they will just be the outputs. So this would be y1 and this would be y2. So let's compare this to what we've already been doing. In previous lessons, we were using squares to estimate the definite integral. Now, coming up with how many squares we have under the curve was a bit tricky, and we would all come up with different amounts of squares because it was kind of hard to have everybody on the same page of how many squares they thought that we had under the curve. It was not exact. So what if instead I could now draw trapezoids under this curve? So let me just give you a couple examples here. What if I drew this trapezoid? Well, that looks like it's doing a pretty good job of, first of all, being tangent to the curve, so following along the curve. And if I knew, which I do in this case, this would be 2 to 3, so the height here would be 1. And I could figure out what my bases are by going whatever the input of 2 is. Well, this height here is 3.9, or I should say that length of that base. And then at 3, my output is 2.7. So I know the lengths of both bases, and I also know my height. Okay, so how does all this come into play in finding the area of a trapezoid? Well, if you remember the way that you find the area of a trapezoid, and there are different ways to set this up. The way that I'm going to do it is we're going to say it's always going to be the average of the two bases. So 1/2 B1 plus B2 times the height. So then I'd be able to take my two lengths of my bases, or my y1 and y2, take the average of them, and then multiply them by my height. Now this gives a really accurate understanding, or I should say a more accurate understanding of the area under the curve. However, it's not perfect. When we have a curve that is, for example, concave down, we are going to get an underestimate because the sides of our trapezoids that we are trying to create to follow along our curve are going to be a little bit shy of the high points of that curve, just like these two appear to be. Still pretty close, and probably closer than squares. When we have a curve that is concave up, we are going to get an overestimate, kind of like we see with my example here, but you can also see the sides of these trapezoids that are not bases, so this extra leg, right, is a little bit above the curve. So it's going to be an overestimate. Now what we're doing here is we are circumscribing these trapezoids into our curve. So let's recall circumscribed and inscribed. So for example, in these polygons down here, this pentagon, this outside one, the circle is inscribed. And on the inside polygon here, or pentagon, The circle is outside, touching the vertices, but so it is circumscribed. Now, what we had talked about once upon a time in geometry was that as the number of angles grew in any polygon, and as it approached infinity, we got closer and closer and closer to 360 degrees. The same is going to be true with these trapezoids. The more trapezoids I draw, the smaller and smaller and smaller my trapezoids get, the more accurate I'm going to be under any curve, being able to estimate the definite integral. Let me show you an example. I'm going to draw a trapezoid, or I'm going to draw a curve similar to the one above. Something like that. I'll try and make it look a little bit like the one above. So right now, I'm a little bit overestimating. Well, what if I drew more trapezoids? So let's start with this one. Right? If I put another trapezoid in there, so now I've broken it up into 2 trapezoids. Now this will be a little bit more exact. That leg might be able to be a little bit more tangent. And then what if I took each one of those trapezoids and divided them up into 2 trapezoids? Think I'm on the curve there. So now I have 4 trapezoids. Well, I think I can get even more exact, or have this leg be more tangent to the curve. So the more trapezoids I have, the smaller those trapezoids are, the more exact it's going to be. All right, let's look at number 2 from your textbook. We've got a walking problem. Pace walker enters an AIDS walkathon. She starts off at 4 miles an hour, speeds up as she warms up, then slows down as she gets tired. She estimates that her speed is given by this velocity function, where t is the number of hours since she started, and v of t is in miles per hour. Okay, well, I think I'll start by labeling my x and y axis here. So this was v of t in miles per hour, and this is t in hours. She walks for 3 hours. We're going to plot the graph of v of t as a function of t for those 3 hours and sketch the result on your paper. And be sure we're in radian mode because we've got a sinusoidal function. Okay, so as I read through this, let's see, B is going to explain why a definite integral is used to find the distance Pace has gone in 3 hours. C is going to estimate the integral using trapezoids. It says to use 6 trapezoids. So how am I going to get 6 trapezoids out of this? So when I draw this curve, it's going to be a sine graph, and I need to be able to divide that up into 6 different pieces. So think about your x-axis. Our x-axis, or our t, needs to be 3 hours long. If I go by a half an hour, then I will have 6 different half an hours in 3 hours. So that's what I'm going to do. And I think I won't label them all. I think I'll go every other one. So this will be 1 hour, 2 hours, 3 hours, but then I've got my half hours in between. All right, so I'm going to now graph that on my graphing calculator. I made sure that I had my function in there. I was in the radian mode. Really what I care about is my table. So I'm going to start my table at 1, and I'm going to go up by 1/2, and I'm going to look at my table. And I'm going to copy these values down for time being 0 hours all the way to 3 hours. And I'm going to go a few decimal places. So at time being 0, she was going 4 miles per hour. She speeds up a bit. 4.6442, 4.9854, 4.8632, 4.335, 4.4 All right, so I'm gonna try and graph those pretty well on my graph. So at 0, oh, let's see, I think I'll go by halves on my y-axis as well. I'm noticing that I'm really close to 5. I don't appear to go any higher than 5, but I'm not certain about that. I'll have to find my maximum. I'll do that in a few minutes. Just plotting the points. Looks something like that. Let's see if I can figure out where my maximum is to know if I need to go up a little bit higher or not. I think I'll calculate my maximum. My left boundary, I think I'll use time being 0. This calculator works a little differently than yours. And my right boundary, I'll use time being 3. And it's giving me a maximum at 1.122, and that's where y equals 5. So my maximum, or her maximum speed, is going to be 5 miles per hour. Maximum speed of 5 miles per hour, just past 1 hour. So my graph will look something like this. Oh, something like that. Okay. So let's see, I sketched the result on my paper. I was in radian mode, all done. Explain why a definite integral is used to find the distance Pace has gone in 3 hours. So finding the area under the curve means multiplying the y values, or the y coordinates, by the x coordinates. And when I do that, if I think about the units, I'm going to have miles per hour times hours. And the hours go away, leaving me with just miles. Let's move on to C. Estimate the integral in part B using 6, or you got an underline there, 6 trapezoids. Show these trapezoids on your graph about how far did Pace walk in the 3 hours. Okay, so I'm going to do my best to draw 6 trapezoids in these 3 hours. And we've already split them up, so each trapezoid, the width, or the height here, is going to be 1/2 hour. So my first trapezoid, got my 2 bases, which are my vertical lines, and then I try and follow along as close as I can. We're going to actually use the numbers in the table, so your trapezoids don't have to be perfect. And you can see that this would be an underestimate because it is concave down. All right, so to do this, I'm going to need quite a bit of space. So we're going to use this table of values, and we're going to work out the area of all 6 of my trapezoids. So I'm going to end up going on to another sheet of paper, but I need to view this table first. So I'm going to start right here. All right, so I have 6 trapezoids here. Each trapezoid I'm going to find the area of. Now notice every single trapezoid here has the exact same height. They all have a height of 1/2. So eventually I'm going to use that 1/2, and I'm going to kind of factor that out to simplify this. But first I'm going to start with actually finding the area of every single trapezoid, 6 of them. So I'll call that T sub 6. All right, the first trapezoid is going to be 1/2, and then I average the bases. So my first base is 4, right? That's the height, okay, or that's the length of that first base. And then the second base is going to be the 4.6. I'm not going to write all these out because I'll run out of room. So I'm just going to write 1 decimal place, but when I do the calculation, I'll be exact. Okay, so I'm going to get 4 plus 4.6 And then I need to also multiply it by the height, which we already said was going to be 1/2. That was my first trapezoid. Now notice those two bases made up the first trapezoid. But when I do my second trapezoid, right, so I just talked about this trapezoid. When I do my second trapezoid, they share a base. They share the side. So what used to be B2 now becomes B1. This becomes B2, and that gives me my second trapezoid. This was my first trapezoid. So adding the area of my second trapezoid, well, the first base will be the same as my second base in my first trapezoid, so that 4.6, plus the next base, which is the 4.9, and then times the height. Okay, third trapezoid, I'm going to use that same base as my first base in my third trapezoid. And then I've got my second base, and then same exact height. Okay, fourth trapezoid, same base as the last trapezoid, plus the next base times the height. Next trapezoid, I think I'm on fifth. 1, 2, 3, 4. I'm on the fifth one. Same base. Then the next base is the 3.6. Same height. And last trapezoid, use that same exact base. And then notice the last base only gets used one time. Okay, so this is pretty complicated, and there's an easier way to write this, and it is known as the trapezoidal rule. So the trapezoidal rule states that if you can recognize this pattern, why not just double the bases that are happening twice, and also factor out the height and this 1/2 that we use every single time to average the bases. So if I factored out that 1/2 and the 1/2 that's my height, I end up with 1/4. So we'll say that T6 is actually 1/4 times. And now what I'm going to do is my first base only happens once, but all the rest of the bases happen twice except for the last base. So I'll do just 4 plus, well, we got 2 times 4.6. Again, when I do the calculations, I'll make this exact. Plus 2 times 4.9. Plus 2 times 4.8. Oops, 4.8. 2 times 4.3. 2 3.6s. And I only have that last base happening one time. So now if I put this into my calculator using the exact values from my table above, I end up with approximately, pace has traveled approximately 13.0206 miles, or approximately 13 miles. Okay, the last part of this is how fast was Pace walking at the end of the 3 hours. We'll start with that one. So at t equals 3, how fast was Pace walking? Looks like she was going 3.1284 miles per hour. They also want to know when did her maximum speed occur and what was her maximum speed? Well, we had said it happened just after an hour. It was this point up here. She was going about 5 miles per hour. So I'll say max speed I think it was 1.122 hours.